Hello everyone, welcome to the first Surge of Deep Learning, part 2. Alright, so in the fundamentals of NLP, we talked a little bit about rule-based NLP. Basically, we talked about a couple of exercises where some knowledge of the characters can help us detect a language, right? So that's a rule-based method. In the previous first deep NLP search video, we talked about neural nets, how they've been applied to language, at least a couple of ways. Neural language modeling. We talked about the advantages of recurrent neural nets. And we talked about the issues with deeper networks that are available these days via recurrent neural nets, namely vanishing and exploding gradients. Today's session, we're gonna pick it up from there, talk a little bit about a couple of remedies to the vanishing and exploding gradients, and talk more in depth about more recent methods in deep NLP. We will also touch upon a couple of statistical natural language processing methods, most likely mostly about the parts that interacts with present deep methods, which is matrix factorization and word representation, for example. Okay, so in the last video we talked about RNNs and the problem of vanishing and exploding gradients. One reason that this problem is kind of exists is because the information that passes through your hidden state, and hidden states, in fact, is unabstracted. And you can imagine that nothing will actually stop these numbers to grow really, really big. So basically your weights can become really big and result into an overshoot in the prediction. And from there, the gradients will also become very large. Now, also, nothing really stops things from going to zero. So the weights can go towards zero and make other representations in the states close or equal to zero, and the signals won't change as a result. So that's a contributing factor. One way we can stop such an issue is using an architecture called long short-term memory. Basically, in this architecture, you have a memory cell that where actually the information passed to or output from it is being gated at each time step. So as opposed to an unabstracted cell that we have seen previously in the recurrent neural net architecture, an LSTM recurrent neural net architecture has gates at a few places. Here they are denoted by the sigmas, you can see. And these gates can stop or amplify information going into the memory cell. So the arrow on top is the memory cell. All right. Aside from the issue of vanishing and exploding gradients, vanilla recurrent architectures had sometimes trouble with keeping the information that needs to be kept. That'll help us in resolving problems called long distance dependencies. Um, a long distance dependency in natural language, for example, is where two items can be very far apart in the language and in the sequence, but they can heavily rely on each other. They can actually be very, very related. Take the case of agreement, syntactic agreement, as an example. So if you say I, and then let's say you can add lots of information about yourself, saying I, a member of such and such society, being from this or that city, um, doing this job, belonging to such company, and then you can say go somewhere. Now, if you replace I with he, everything else untouched, then the verb go has to agree with the word I, right? So that's a long distance dependency. And your network is required to keep the information regarding I or he or she, the subject, and carry it over all the way to the verb through all the complementary pieces of the sentence. LSTM architecture is also a remedy to that. Basically, these gates can amplify certain items in the sequence and make sure they're present, the information of which is present in the memory cell, and make sure other parts of the sequence, for example, that don't rely on anything else, are trivially included in the memory cell. Okay. You basically have three gates: the forget gate, the input gate, and the output gate. The input gate gates the input information coming from XT and coming from the hidden state of the previous memory cell, the previous state. The input gate gates the information going from X, at time T, the present input, and the previous hidden state, to the current state of memory cell. All right. And finally, the output gate gates what comes out of memory cell to construct the hidden state, going to the next state. So the information that comes out of memory cell is also gated. These cells get repeated at each time step, and the weights are shared, just like a vanilla recurrent neural network. As you can see, your forget gate and your input gate, they both receive information from ht-1, the hidden state of the previous time step, as well as the present input, xt. They have their own biases, and also they have their separate weights. So the weights for the forget gate obviously are different from the input gate. Hopefully they perform different tasks. Okay, so that's the forget gate and the input gates. So C tilde T is the candidate cell, candidate memory cell at time T. It's right over here before it's input to the memory cell. Basically, it's a tanh activation function applied to its own weights and ht minus 1 as well as xt, the hidden state of the previous step, time step, as well as the present input. It obviously also has its own biases. The purpose of this is to come up with a memory cell, a candidate memory cell. Great. So now we're at the crucial part. To get the present memory cell, remember, the memory cell is the link between the present time step and the entire history. It's a more reliable source of information because of all the gates. All right, so the present memory cell is then a combination of the past memory cell and the present candidate memory cell. Obviously, the candidate memory cell, we have to apply the input gate to, because it's getting input to the present memory cell. And ct minus 1, the past time steps memory cell, needs a forget gate to apply to it, because there may be information that we don't want to carry over to the present time step. Pay attention to the fact that your gates, your forget input, and you see shortly the output gates, they use sigmoid functions, and your candidate memory cell uses a tanh function. So the range would be between -1 to 1 for these, for this one specifically, and for the sigmoid functions, the ranges are between zeros and ones. Well, 0 and 1. Okay, so what's the output gate? The output gate is right over here, as I've mentioned previously. It has a sigmoid activation function to force the values to go between 0 and 1. It has its own set of weights. And it is again a concatenation of ht minus 1 and xt. These square braces are the concatenation functions. Okay, it also has its own bias, obviously. So what does it do? It basically constructs the present ht, the hidden state at time t, which takes in the present memory cell, runs a tanh activation function on it, and mitigates the information using the information passing along to the next memory cell, well, to the next state, using the output gate at time t. And here it is. Okay, with that, you know exactly how LSTM works. Now, let's talk briefly about autoencoding in deep learning and its significance. Autoencoding is a very smart way to bridge the gap between supervised and unsupervised learning. It can result in a concept called representation learning. In autoencoders, basically what you do is you have your input, could be any sort of data inputs, any set of real data inputs, and then you use feed forward. Here, for example, you're using feed forward. You can use other types of neural nets, but originally feed forward networks. You can use a feed forward architecture to compress information into a bottleneck and get a latent representation. And then you would have another layer, another feed-forward layer, to generate the original input. So you can see that you don't need any labels because what you're generating is the input that you already have. So you don't need labeled data to backpropagate the error. All you need the input, which can easily construct your cost from comparing the present output, the estimated output, and the actual input. Here, x hat and x. So autoencoders can be construed as a dimensionality reduction algorithm that have quite a few advantages over pure matrix factorization. But before I get into that, let's talk about the advantages of creating such compressed representation. In natural language processing, this kind of representation and representation learning is very valuable. Think about meaning and understanding. Having a representation that signifies words and their interactions, or signifies sentences and their interactions. In classical NLP, rule-based NLP, we have this construct called WordNet, which is a graphical representation of the relationship of all the words in a language. It's very hard to create because humans have to sit down and draw the graph. If you have such a system as an autoencoders, for example, to understand the meaning from text, then you can infer the distance of words and the relationship of words without having to draw them in a graph manually. And hopefully all you need to do is to have your input data. So that's only one direct application, but there are many, many other applications, including threat detection, cybersecurity, outlier detection, removing noise, and generating every type of data, tabular, text, or images. They all rely on the principles of autoencoders. Autoencoders are great replacements for their previous counterparts, which was matrix factorization methods, such as SVD or principal component analysis. They could, to a good extent, achieve a similar task of compression of information. The issue is they are memory-intensive algorithms. That is, in order to create such a representation, you need to store a co-occurrence matrix that holds every interaction of every items in your vocabulary. For language, you can see that it becomes really big easily. For example, if usually speakers of languages have tens of thousands of words in their vocabulary. Now, at least you would have something like a 10,000 by 10,000 matrix to store all the interactions between words if you want to have a word representation, for example. And you got to keep that in memory and then factorize it using matrix factorization methods. With the present cloud computing methods or cloud computing resources, it's not as daunting as a task as it was before. It can still be done. But when you have a more efficient method, why not just use a more efficient method, including autoencoders? So in short, autoencoders are a definite improvement over pure matrix factorization methods, which belonged to the statistical natural language processing era. If you want to put everything in a timeline, if you remember, basically we had the rule-based era, which was followed by statistical natural language processing era, and then the first surge of deep learning in NLP and the second surge of deep learning in NLP. If you'd like to know autoencoders more closely and in more detail, I've included a document and the resources in the student materials directory for you to see various types of autoencoders and a few applications. The same concept gave rise to the encoder-decoder architecture. It's a very interesting architecture. It enables natural language processing algorithms not only to understand natural language, but to generate. This can be directly applied to machine translation, for example, where you have an input in one language and another, and you'd like to produce the output in another. Another area of application is conversational agents, for example, where you have a question and you'd like to generate an answer. Basically, what happens is that you run your LSTM network, and it acts as your encoder. And one way or another, you end up at a representation. Sometimes it's only the last hidden state or the last cell state. Sometimes it's an average. And sometimes there are more advanced methods that we'll talk in the future videos. Anyway, you gather that information, that compressed set of information that represents the entire input sequence. Then you input it to your decoder. You have your LSTM encoder, you have LSTM decoder. And the decoder's task is to grab the representation achieved in the encoding stage and generate the output at the decoding stage. Everything else is almost exactly identical to LSTM architectures. This variation of encoder-decoder architectures or autoencoding, it's different from autoencoding because it's not the output and inputs aren't exactly the same. They're actually different. That's why we call them encoder-decoder architectures. But regardless, this variation of encoder-decoder architectures are called sequence-to-sequence models or seq-to-seq. The reason for that is you have a sequence as input and you'll have a sequence as output. And there is time dependency that is meaningful. Now, Micallef et al. 2013 discovered a more efficient way of encoding words. So if you remember the neural language model, you can actually use neural language model to create embeddings or word representations. If you remember the projection layer, that projection layer can be trained such that the words that are closer to each other in the semantic space are actually algebraically closer to each other in the vector space as well. All right, but that's a very costly way to train it. Using a similar architecture, but much shallower. In fact, it's a shallow architecture. It doesn't have more than one hidden layer. You can come up with word representations. On the left, you see your SIBO architecture, and on the right you see the skipgram architecture. In SIBO, you have your words surrounding a target word. It's a simple summation of the surrounding words. So each one of these is a vector. And that constructs your present word, your target word. So in sum, basically, you have this shared projection layer that's shared for when processing all the words as target as a target for this architecture. That projects the surrounding words, the context words, within a window to a single projection unit, then outputting a representation for a word at time step t. This entire process is a log linear process. There are no nonlinearities. In the skipgram architecture, you take as input the target word, then you try to estimate the surrounding words. The premise behind these methods is that a word is nothing but a combination, some linear combination of its surrounding words. So throughout the method, whether it's predicting a target word, single target word, or multiple target words, the algorithm uses a hierarchical softmax architecture, where the vocabulary is represented by a Huffman binary tree. This obviously significantly reduces the training time to a log of the initial cost. In the student material directory, you have documents talking about the hierarchical softmax layer, as well as Huffman binary tree for a refresher. Feel free to take a look. Now, one question is that you're only generating positive. You can only predict positive. You have only as labels positive instances. You only know that if you're generating WT, you only know what's the right word to generate in this context. But what about negative instances that are also required for learning? For that, the system, well, the algorithms use noise contrastive estimation, where you sample from other words that do not occur in the context and feed them in as negative instances. So here we have it. Log linear, highly efficient word representation algorithm that doesn't need to go through layers and layers to create word representation. Now, where it fails is where you actually need nonlinearities. If you remember from our examples with the dot, rat, and mat, these nonlinearities do occur in natural language processing very often. For example, in pure Word-to-Vec, the word good and bad are very similar because they usually occur in a very similar position. There are ways you can go about it aside from adding nonlinearities, but nonlinearities is the right way to approach it, and the most effective way to tackle that problem. All right, let's talk about GloVe. GloVe at the time outperformed the Word-to-Vec algorithms. Basically, Pennington et al. 2014 found a way to reconcile the gap between matrix factorization methods and the more modern neural net approaches. The idea behind it is that approaches such as Word-to-Vec only locally construct the representation of a word. Basically, in Word-to-Vec, you have a context window that you can go only a few number of words in the future or in the past to form the representation of the present word. Whereas words can actually, in a page, in a document, can occur much frequently together. It's just that because they don't occur in a very small window, they occur in a bigger window, you lose that relationship. Now, there are arguments that that relationship can be captured indirectly, um, but that's a hard task. Regardless, their Glove's premise was that we can still build the big co-occurrence matrix without having to factorize it at once and entirely. Basically, they propose a smart sampling method to sample from the co-occurrence matrix. Specifically, they stochastically sample from the non-zero elements in the co-occurrence matrix X. They utilize a simple least squared regression method that's weighted by this function f. This weighting function f has a few constraints that, they came up with the function using the constraint. You can see they list the constraints in their paper. I've shared their paper in the materials folder for you to take a look if you'd like to. But here's what the function looks like. I always like to see functions visually. Basically, there's a max, there's a threshold that when you reach, after it, it's just constant. Before that, your weighting is monotonically increasing. Now, let's take a look at what's happening here in the cost function. So basically, you have two words, I and j. They can simply represent a cell in the co-occurrence matrix. You have their corresponding biases. And you are computing the dot product of the two. And you're subtracting all of those from the xij, which is the frequency of co-occurrence. How many times simply they co-occur. What's going to happen is if their similarity is high and they co-occur a lot with each other, these terms are gonna, to some extent, cancel each other out, and you would have a smaller cost. Now, and that's a good thing, because if your representations are already loyal to the co-occurrence, then that's a good thing. And similarly, if their representations are nothing alike, so that's a very low number, and the frequency is also low, again the cost is small, so you're at a good spot. However, if one of them contrasts the other, you would have a greater cost to retrain the network. All right, so that's GLOVE with sampling from the co-occurrence matrix. You have some more global information about the words that co-occur with your target word, not just the immediate ones. Therefore, it has a better performance. This brings our first surge of deep learning in NLP to an end. You will learn more about the second surge of deep learning in NLP very soon. Thanks for joining. See you in the next video.